So thanks for joining me today, folks. So today I wanted to spend just no more than 15 or 20 minutes talking to you about system level modeling and more specifically ways that you can drive an adoption of this process in your company effectively. We've done a bit of commissioning of some research over here at Maplesoft, and we wanted to share with you some of the results of that. It's going to be nothing that you may not have already have thought about, but hopefully I'll try to crystallize it in some ways that'll help make a difference in the companies that you work for. So when I think about system level modeling, we think about it in terms of ways that can make innovation really more effective. Because innovative designs, they carry risk. They're trying to create new designs that are pushing the edges of what you've already done and trying to try out new designs. And a lot of the risk involved there is especially at the time when you're trying to bring new subsystems and new components together. So the prototyping and integration phase, that can be a very expensive phase, and for our customers, that tends to be one of the highest risk phases of a design, especially a new or innovative design. So these are fundamentally system level issues. So these are issues that have to do with perhaps a failure to understand what the entire system of your design is doing. So system level modeling and the way that that can help, this is a modeling process that is trying to capture system-wide interactions. So this is going to span a variety of the domains that's going to be in your product. So it'll take your mechanics, take your multi-body, it'll take the thermal components, and it's trying to capture all of that in an integrated fashion instead of breaking it out into different tools and then trying your best to somehow have that data speak to each other. And system level modeling really helps organize the design knowledge across teams. And the teams are going to be working on different parts of a design. So especially large, complicated designs are going to have a huge amount of complexity in only, say, one part of a design and one subsystem. So taking on a system level modeling approach, it just helps make that a more cohesive process. And the purpose of that, at least one of them, is to spot problems in the design process earlier. So you don't have to wait until, say, the integration phase. It also is going to help reduce the expensive iterations born out from, say, prototyping, the kind of FEA work that might be involved. Of course, FEA is very important to do, and that can really help with specific parts, and it can help give you specific information you're going to need. But with the system level modeling approach, you're going to be able to gain some insight onto exactly what local area you're trying to optimize with certain FEA processes, and you'll be able to do so in a very resource efficient way before you start dumping a lot of resources into an FEA process. One piece of literature that we use here, we talk a lot about virtual commissioning and how using system level models can really make this process of commissioning happen in a much lower risk way. So virtual commissioning is taking the standard commissioning or integration phase of a product, but when you're, say, caught up in doing control design, you can develop your controllers based off the system level model. So you're going to ensure that they're going to be more correct the first time. And then when you start to actually put all these controllers onto hardware, you can start to test the different aspects of your design and the different components against these virtual parts of your model. So by doing that, the results have been great. Commissioning time can be reduced hugely, up to 75% by this research. So ultimately, system level modeling is here to reduce the risk and the time required to innovate. It's a way to help you test out new ideas and to lower the risk of trying to make those new ideas a reality. And one of the ways to think about the risk involved here is to think about the cost of design changes. And as you move through a typical design process from concept through to prototypes and then a release to market, if you find something in your design that you're going to need to go back and you're going to need to make a design change for, the cost just continues to increase because you've already sort of been committed along a certain path of design. So to be able to change something on the concept level is fairly inexpensive. But as you scale through to prototype and production and even release to market, the costs just increase exponentially. And with a system level modeling tool, the issues that you identify are going to be in the earlier phases of a design process. And that's typically when they're the easiest to change and they're the cheapest to change. And without a system level modeling tool, and of course system level modeling won't catch everything in a way that somebody's typically going to use it, but the issues that are going to be identified later without system level modeling tools, they just stand to be very, very expensive. And this is really the justification that a lot of our customers have used to go ahead and drive some adoption of this in their company. Even if they're able to save out on one design change in the production design area, that has already justified all of their costs for working a bit harder at a system level modeling approach. And there's this other piece of research that was showing that when companies would allocate 5 to 10% more of their budget to early design work, which is included with system level modeling, this can actually help reduce project cost overruns by 50 to 100%. This research was taking a wide variety of programs that NASA had run over the years and reliably would show that if they just put a bit more money up front into their early design work, that the cost overruns decreased dramatically. So 3 adoption strategies I wanted to talk to you about. They're strategies that were the results of that research that we commissioned. And in some sense, they're nothing new, but these are the kind of strategies that are the most effective to think about when trying to drive a process like this in your company, because they're really the strongest justifications for what system level modeling can do in your design process. So the first one being to try and quantify the risks. And of course, you're not going to be able to do that specifically, but trying to at least put some rough orders of magnitude on the risks can really help paint a picture for your organization. A story about that with a company that we worked with was FL Schmidt, and they develop really large mining equipment for that industry, and they were trying to create a new design. So again, they're trying to do things they hadn't really done before, just sort of an iterative innovation on what they were doing. And they came to us to help them build a system level model to simulate what that new design might actually look like in its dynamics, and if it was going to be possible. And what we helped them find was that their typical hydraulic system that they had continued to use for a while, it was going to be ineffective for this design. It actually wasn't going to work. And although perhaps they would have found that down the line, we were able to find that problem with them just at the concept level during this modeling process. And then they were able to find something that worked. And essentially what they were able to do was mitigate the risk of having a huge costly mistake down the road and find that out early on. The development manager at FL Schmidt was very happy with this, and they've continued to use the software. And in their words, it already in just helping reduce the risk of this one design iteration, it significantly reduced the development costs just from that angle. So really trying to think about how the risks look in your typical design process and what it might look like even if you could knock one prototype iteration out or take out 50% of the time, 20% of the time that you might spend in a later stage design cycle. Another strategy is thinking about how investing early into training and model-based engineering services, how that might look. Like taking on any kind of new technology or process, you might be lacking in a little bit of internal expertise, and you might feel like the appropriate path forward is to invest heavily into having your own internal engineers become their own experts quick and develop these models from scratch. And it's likely a good long-term strategy, but we've worked with some companies where they've come to us and we've worked with them to sort of hand them a good variety of the materials they need to start seeing results in that project. And then we help them forward so that they can continue to do that on themselves going forward. So we've got this example from the automation sector doing that. This company we worked with was trying to create a new style of packaging machine, and we helped them create a system level model to understand the dynamic controls around that and how all the loads looked, and help them size their motors properly given the motion profiles that they were hoping to use. So we were helping them create a better packaging machine. And what we helped do with them is we created that model for them, and we were able to deliver a working model to the fidelity that they required, and some purpose-built applications that helped them size their motors and that helped them see the dynamics involved. And this was before they had their own expertise at system-level modeling. But the great thing about system-level modeling, and especially our software MapleSim, is you can build these purpose-built apps that really don't require the expert-level modeling experience. Once those models are created and we've helped validate them for you, these apps allow you to get the work done you need to do without needing to dig right down to the fundamentals of it. Another benefit, too, of this particular story was by having all these simulation results, the packaging machine was able to be made with less physical sensors on it. And that's because a lot of these sensors in certain automation equipment, they're there to help get real-time information about the loads experienced. But really, if you had a good system-level model, which they did, you can kind of run the math on it, and you know based on the machine's operation what the dynamic loads are going to be at a certain joint, because there is just math to demonstrate that. So with a good model in hand, not only did it help them design it better, but as they were to use it, they were able to see the loads at different joints. So it helped them down the line for maintenance and diagnostics in a cheaper way, less sensors. The third one I want to talk about is, again, it's trying to roughly estimate your ROI. And all three of these strategies are things that you may have likely considered. But the way we see it is these are realistically some of the most powerful justifications for trying to adopt some amount of model-based design in your organization. So this one is sort of related to the way to quantify risk. And I'll walk you through with another company that we worked with. And this one was a company that they managed they managed wind farms and all the maintenance involved. And to do that well and to have that a cost-effective kind of business model, they're trying to minimize the downtime on all these wind turbines. But every wind turbine is different. It experiences different amounts of wind. All the parts may degrade at slightly different amounts. And we worked with them to find the accurate lifespan of the ball bearings in each individual windmill. And we were able to iterate through a lot of design configurations to help find an optimal model for this and find ways that it would be different depending on the inputs, depending on the specific wind farm and wind turbine. So what that was able to do was they essentially had this term that's appearing in industry more now. It's a digital twin is what we call it. For us, we call it a physics-based digital twin because in industry right now, when people hear digital twin, they can tend to think a lot about the model and the twin you have after the product is done with a whole bunch of sensors, and then through a lot of information it gets processed in the cloud and some predictions come out. But we try to capture a lot of what you can do there before the product needs to be shipped out. So we call it a physics-based digital twin because with the right physics in place, you can capture most of that information if only you just know technically what's going on in your product. So they had one of these. We helped them make one. And they're able now to forecast maintenance so that they know to a high degree of accuracy when those ball bearings are going to fail. So they don't have to over-maintain and lose out on operation of old parts, but they don't have to wait now and experience large amounts of downtime. So the ROI there was pretty clear. The ROI is almost considered, it's almost like there's two different categories you're thinking about here, because they were considering some upfront investment in some software and some training services. But the kind of model that we were able to provide them, these things tend to have ongoing lasting value because although it's going to be effective for one project, it's going to save them a lot of maintenance. Models that we help companies deliver and that we give over to them, they typically become healthy foundations, not only for that one product, but then that company is able to iterate on that and they're able to use that as the foundation for future projects. So there's a lot of lasting value in these things, and they end up rolling into being effective for innovative products down the road. So moving on now to the way things might be currently done in your organization and where we see system level modeling fit, not only in just making your ROI better, but all the ways in which taking a system levels approach to a design process actually can just smooth over a lot of the inefficiencies or difficulties of a traditional design process. One of these traditional ways that most engineers will find themselves in at one point or another, it's not necessarily all bad, but there can be an over-reliance on just disorganized scratch pads, on derivations just done by hand on the back of a napkin sort of thing. And while this works, and it typically works because it's the most intuitive way that the current engineer has, it's just what they kind of default to, there ends up being a lot of lost design knowledge along the way because of that. These things don't typically get recorded in a way that easily survive an engineer switching companies or somebody moving on. And the same kind of goes for spreadsheets. While they have many great uses, there's an over-reliance there, just born from the fact that most people are used to using them. So once again, there's those notorious spreadsheets that have long and complicated formulas, and it's hard to see how they're documented. So these things just tend to slow down the team's ability to make smooth, effective processing or smooth, effective steps forward. Again, when the reporting phase comes in and there's different engineering analysis reports to do, and they may not have really traceable lines back to where those derivations or those design processes came from. So it can be hard to audit them. And black box design code is essentially meaning that as you're developing controllers, as you're working through different parts of the conceptual design process, things might find themselves into a variety of different code, and the traceability there can be very, very hard. Certain code is very hard to read through. And these four things, they're essentially just putting up little blocks or little locks between different steps in the design process. And while that might be fine in an organization that everybody knows their place and they communicate well, the stability or the sustainability of that process, it continues to be in jeopardy, especially as evolutions take place and as engineers move on. So not only do we create a system level modeling program, we try to take all these things in mind when we created MapleSim. And we view MapleSim not only as a really powerful system level modeling tool, but we view it as an ability to help unify the design process in many ways, because the system level model and all of the analysis that can come out of it, it can really serve as the foundation for a lot of the tasks that will end up happening in the design process. And it's not that it becomes an all-encompassing tool that always has to be used by everybody, but it becomes a very consistent set of defining the product in a model-based way that can be easily changed by a variety of people and can have analysis tools deployed from it that will still maintain a connection to the model itself. So it becomes a great way to have a process that can be updated quickly and be iterated fast without the risk of having a spreadsheet not update in the right spot. So it's a very consistent way to do product design. So just getting to the end of it here, how we really conceive of what we do is removing the risk from innovation. For every product design that is striving to create something new and to push the limits of what they may or may not be able to do, the risk is going to continue to increase. And our host of products and services are designed to help reduce that risk along the way. So we've got MapleSim, and that sits on top of our mathematics software Maple, which is an end-to-end environment for calculation management. So that can capture so much of what a typical engineer will do with their calculations in a really intuitive way, and it works directly along with MapleSim in that modeling environment. And there's a bunch of different toolchain connectors and add-ons, as you can see, but all of this really wraps up to a variety of products that we offer alongside our engineering services. So that's really useful, like I demonstrated in one example. If you have a problem that needs to get solved and needs to get solved fast, you could try and develop that expertise internally quickly, but we've worked with companies where they need a model and they need an answer in just a couple weeks. And in a turnaround time of only about 2 weeks, we could figure out the kind of product that they need help with, and we could deliver them a model and a purpose-built application for their particular problem. And then as the months go on, they can kind of make a more robust model for a larger product design. But our engineering solutions are designed to help get your specific problems solved as quickly as you need them to, and then we can move on to the training and to developing more robust modeling processes in your organization. And some of the adoption challenges are similar to what any company is going to face when they're trying to take on a new technology. They may not have the internal expertise. They may be concerned that the way things have been done will change to a degree that they're just not going to get buy-in within the organization. And they already have a bunch of software tools that they're paying for. They may not even use all of them. And they're hesitant to bring on another tool that might just sit on the shelf or might not even connect to their other tools. So we've really tried to address these things. We've addressed the internal expertise, like I talked about, with the training and engineering services. So no matter what background you have with modeling or even system level modeling, we have training programs and we have services to meet you where you're at so that whatever problem you're facing can actually be solved quickly, and then we'll go from there. And MapleSim really, it works alongside current processes. Our goal is not to displace the FEA or CAD happening in your organization already, or to displace the prototyping phase. What we try and do is provide you a time early in the design phase at that concept level to put a little bit of work in up front so that all the subsequent phases, you've got a much better starting position so you can hone in with FEA better. Even if you're working with some CAD can speak with MapleSim back and forth. We can take CAD models in, help get that model started, and we can shoot out good dynamic information out. And we also make sure that it's able to be connected to a variety of leading tools. So if you need to get stuff automatically into spreadsheets, into C code or Simulink S functions, the list goes on. It's something that we know is very important, and we try to make sure that MapleSim can connect wherever a typical engineer needs to move next in their design process. So I know that these were 3 strategies that came out of that research we commissioned, and there was no silver bullet there, but you weren't expecting that anyway, I hope, because the truth of the matter is that there is no silver bullet for that, but these are really the 3 strongest ways to justify making that move, and we've tried our best internally to develop strategies to help you work around those 3 principles.